Hi, in this video, what I want to do is talk about another module of Atmega 328, and this module is called the interrupt module. Uh, One of the ways to start thinking about the interrupt module is to imagine a scenario. Okay, imagine that you are watching a movie in your room and you have put headphones, and because the movie is like a kind of uh, a loud movie, probably an action flick or something like that, so the volume is very high and you're just watching it and you're totally engrossed in it and you're enjoying it. But at the same time, you know that a friend is going to knock at your door at some point while you're watching the movie. So you have put your headphones on, and but when you're watching the movie, you can't really hear the doorbell. Okay. So what do you do? Okay. So how do you actually uh, monitor the doorbell while you're watching the movie? Okay. This is very similar to what to a question that you could to a scenario that you can imagine where a robot is doing a work doing some task, and he's waiting for input from somewhere else so that he can respond to it. So the robot is completely engrossed in doing his task, but he needs to respond to some other input that comes in. Okay, so here's what I mean. So in this slide, I have these. Imagine that these boxes are showing you a sequence of things that you want to do. So in your case, it is basically putting the earphones on and watching the movie. Okay, and while you're doing this, you don't have any room to look for other inputs. Okay, you're just engrossed in doing this. So you finish this, and then probably you can look at uh, to see whether the doorbell is ringing or not. But let's say you know that an input is going to come, that the doorbell is going to ring. One thing that you can do is you can watch a bit of the movie, let's say 30 seconds of the movie, and remove the headphones, and then just listen for the doorbell. You say, oh, there's no doorbell, put it on, watch another 30 seconds of a movie, remove it, and then just listen for the doorbell. No, there isn't. You could do something like that. Now, this kind of phenomenon, just imagine a robot doing it. How would that it look like? So basically, you have these series of things that series of code that a program needs to execute or a robot needs to do, and then you have this new task that has come that needs to interrupt the regular flow of activity that the program is doing. Okay, again, looking back at the analogy, the regular flow of things is you watching the movie, and the interrupt is basically responding to the doorbell, right? So how would you respond? One of the things that you can do is, as I suggested, after every line of code or after every 30 seconds of watching the movie, you could stop, go and see whether there is a doorbell, and if there is, you can execute this and come back and watch the movie. Or if there isn't, you just continue and do the next task. Does that make sense? So you run this line of code, you do a small bit of activity, and then you check whether an input has arrived and if you need to respond to the input. If that input has not arrived, you can go to the next line of code, and then you again wait, again check for the input. If the input has arrived, you execute the input, you respond to the input, come back, execute the next line, and then continue. Okay, this method is called polling. Okay, polling is a protocol that keeps checking to see whether the input has arrived. Now, what are the problems with polling? As you can imagine, one is that it increases the amount of work that you have to do, right? Because every 30 seconds you have to remove your headphone, listen for the doorbell, put it back on, and start all over again. Okay, in a program, you have to execute a line of code, you check whether the input has arrived, and then you execute another line of code and again check whether the input has arrived, and so on and so forth. And that increases the amount of work that you're doing. Another problem with uh, polling is, what if the doorbell actually rings when you have the headphones on, right? So the doorbell rings, but you have your headphones on, you're watching the movie, and it switches off before you take off your headphones again. So you will completely miss the input that is coming in. And that's the same thing that happens with programs as well. Okay, so what is the solution? Let's take a look. So the solution is to have a separate bit of hardware, okay, uh, which can help you do this. Now, here's what I mean. Let me go back to my movie watching analogy. And suppose you take an additional bit of hardware, and here's what you do. You connect your doorbell to an LED that you put right on top of your computer screen or your television where you're watching the movie, so that the LED is in your field of vision. Okay, so so you can continue watching the movie, and when the doorbell rings, the LED lights up. Oh, and you can see that as you're seeing the movie. And so what you can do is you can respond to that signal. So what have we done here? What we have done is we have added a bit of hardware so that it helps us to respond to inputs. Okay, and that's exactly the thing. That is exactly the same thing that we do in microcontrollers. And this extra bit of hardware is, and this method of kind of interrupting your regular, uh, the regular process that you're doing by adding an extra bit of hardware is called interrupts. Okay, so that is another way of responding to inputs. It is different from polling, which we looked before. So an interrupt is a hardware mechanism that enables the CPU or the processing unit to detect that the device needs its attention. Now, how does that work? So imagine that you have something called a program controller in the microcontroller. Now, every microcontroller needs to have a program controller. What does a program controller do? A program controller just tells the microcontroller which lines of code to execute. So when this line is being executed, now where will this code be? It will be somewhere in the memory. Okay, so the program controller tells it, okay, at this memory location, there is a line of code. You need to execute that. You need to do that thing. So, uh, so basically, that command from that address is fetched. It is executed, and then the program controller increments by one and says, "Let's go to the next memory location and take whatever code is there and execute that. Whatever instruction is there and execute that." And then the program controller goes again and goes to the next program location, and so on and so forth. Okay, so the interrupt mechanism uses this program controller to help us to respond to input. Okay, now imagine this. You have this lines of code, which is kind of in the main routine, the task that you're actually doing. And this is the task that you want to do when the input arrives. Okay, so here's how this functions. When an interrupt arrives, the program controller, instead of asking the microcontroller to execute the next line of code, tells the microcontroller, it says, don't execute this one, go and execute these lines of code first. And after you have executed this, you can come back and execute these lines of code. Does that make sense? So so a program controller basically directs the microcontroller usually to just execute commands which are one after the other in the memory location. But in response to an interrupt, what the program controller does is it says, oh, let's not execute the next line of code, but let's go to what is called the interrupt service routine, or the code that will respond to the input, and let's execute that, and then we can come back. Okay, so as I've said, this is called the main program, and the code that is a response to the interrupt or is a response to the input is called the interrupt service routine. It is the code that is executed when the interrupt comes or when the input comes. Okay. Now, of course, one of the problems with this entire idea is that when the main program is running, there is some data that is associated the with the program, right? So imagine a very simple task. So, for example, imagine that you are just adding an array of numbers. Okay, so when you're adding an array of numbers and you have added a few, let's say five of the numbers, you have the sum that you have in your memory. You also have the position in the array till where you have reached, uh, and you don't want to lose it when you are going to respond to the input. So basically, you need to save these variables that the main program is acting on somewhere. Okay, in other words, you want to save the environment safely so that when you come back, you can respond to the input. Another way to put it, if we take our analogy again with watching the movie, is when the LED flashes, you want to pause the movie at that point. Okay, and you want that position of the movie to remain there. But not only that, you don't want to forget what had just happened. Otherwise, you'll have to kind of watch the movie all over again to kind of remember it, right? You want to go and respond, you want to open the door, you want to come back, and you want to start exactly where you were, ideally, probably in the same emotional state. But at least you want to remember where you were in the movie, right? So you want to store the context, store the memory, the CPU environment safely while I go and respond to the input. So, uh, so how do we do that? So to do that, let's take a look at yet another concept, the concept of a stack. Okay, so here's our main program which is running. Here's our interrupt service routine which we need to respond to when this interrupt arrives. So we are executing this code, and this code has this context associated with it, which I have shown in blue. So what I can do is I can take this entire context and put it in another memory location, which I'm calling the stack. Okay, so the interrupt arrives and there is a context associated with it. I put this context in the stack, and then I go and execute my interrupt service routine. And once I finish executing my interrupt service routine, I come back to my main program. I then bring back my environment or my context from the stack and then start executing the next command. So that's the way the interrupt service routine would work. Does that help you to understand what is going on here? How we are able to start at exactly the same place where we left off before we went to execute the interrupt service routine in a microcontroller. Now, what does the interrupt service routine do? Can it change something in your program? Yes, it can. Okay, and the way you do it is by using global variables. So what I mean is there are some variables that you can access from the main program and from the interrupt service routine both. Now, if you want this interrupt service routine to change the way you're running the program, okay, so for example, you're watching the movie, somebody rings the bell, you go and open the movie, and somebody says, well, in 15 minutes, let's go to have a coffee. Okay, you come back and you see that your movie has 1 hour left. So what you do, you kind of fast forward the movie and watch it. Excuse me. So you fast forward the movie and you watch it. So your interrupt has modified the way you're executing the program. But how would the interrupt service routine actually communicate with the main program? It communicates with the main program by what are called global variables. variables that both the interrupt service routine and the main program can access at the same time. Okay. Now, there are a lot of interrupts in Atmega 328, and of course, there are some external interrupts, which means some signals that are connected to the microcontroller from some external devices can cause an interrupt in your program. But I think some of the interrupts that we would be concentrating in our module would be the timer interrupts. Okay, so for example, remember what we talked about timer overflow? So here's a interrupt which happens whenever the timer overflows. So whenever you have a timer overflow, an interrupt is generated. And you can code such that as soon as the overflow happens, you want some action to happen in your microcontroller code as a response to that. Similarly, you have uh, uh, interrupts which respond to the ADC conversion. So for example, here there is a interrupt called ADC conversion complete. So whenever the ADC conversion finishes, you can have an interrupt saying, okay, let's read the ADC value now from the ADC output registers, right? So those would be two of the interrupts that we would be using quite a bit in this module. But again, there are lots of other interrupts that are available that you can use for different applications.